Okay, so it is 11 o'clock, so I'm going to go ahead and get started. Hopefully everyone can hear me okay. If you cannot, tell me in the chat or unmute yourself or something. I don't care. Feel free to interrupt me at any time. Any questions you guys have. As always, I do not mind being interrupted. Um, I'm just going to talk to you guys today about empirical molecular formulas. So normally I watch what my colleagues show you guys earlier in the week, but to be honest, it's just been a really busy week and I haven't had a chance. So this is what we're supposed to cover today. So hopefully this will be helpful review for you guys. If you have seen it, if you haven't seen it, hopefully it's a good introduction for you. So empirical molecular formula, what do I mean by these things? Empirical formula and molecular formula are really important in chemistry because oftentimes we're trying to identify an unknown. Like, what do we have? What is this substance? And one way we can do it is we can actually analyze a sample to figure out what it's composed of. And then from there, we can figure out its actual formula. So the difference between molecular and empirical, a molecular formula is something that's going to show me every atom that's an element. So it's showing me the entire formula of that compound. That doesn't mean it's always telling me the compound, because some elements or some compounds, some molecules will have the same formula, but a different connectivity of the atoms. We're going to see that a lot, a little bit in Gen Chem 1 specifically, more in Gen Chem 2. When we get to the end of Gen Chem 2, we do an organic unit, and then definitely inorganic. Sorry, hit the wrong screen. Definitely inorganic when you get there. They're called isomers. So compounds can have the same formula, but a different connectivity, different compounds. But molecular formula still narrows down that field a lot for us. So again, molecular formula, the number of atoms of each element in a molecule. For example, the molecular formula of benzene is C6H6. There is 6 carbons and 6 hydrogens in a benzene compound. Empirical formula, on the other hand, is defined as the smallest whole number multiple ratio of elements within that compound. And so this phrase is something I use a lot in class. I'll say, smallest whole number multiple ratio. And I know that, yes, it is the definition of it, but it's also how I have memorized empirical formula, because that's what clues my brain in on what math to do for the system. I'm looking for whole numbers, I'm looking for multiple ratios, and I want the smallest of those ratios. And that's what reminds me what math I need to do to figure it out. So for example, what's the empirical formula of benzene? If the molecular formula was C6H6, but I want a multiple ratio, and remember when we talked about this last week in chapter 2 content was last week, we said, this is showing you your ratio. We've got 6 carbons to 6 hydrogens. The smallest whole number ratio for that would be 1 carbon to 1 hydrogen. So the empirical formula of benzene is CH. Why is that helpful? Again, I'm going to show you, we're going to do some examples here in just a second, but we can often calculate the empirical formula and then find a different way to analyze the molecular formula, and we can then figure out what the compound is. So let's work some examples. First one, a compound of nitrogen and oxygen is analyzed. A sample weighing 1.587 grams is found to contain 0.483 grams of nitrogen and 1.104 grams of oxygen. What is the empirical formula of this compound? So I know, what do I know from the start? I know that I have some type of nitrogen, or not type, that's not what I meant. I'm not talking about isotopes here, but some amount of nitrogen in the compound and some amount of oxygen. I can see that my total sample is 1.587 grams. I've got 0.483 grams of nitrogen and 1.104 grams of oxygen. By conservation of mass, if I was to add up that grams of oxygen and that grams of nitrogen, it would weigh 1.587. It has to. I cannot create nor destroy things, conservation of mass. So that's what I know going into it. But I want to know the empirical formula of this compound. Now's when I'm going to go back and I'm going to think about that definition of empirical formula. So I know I'm looking for the smallest whole number multiple ratio. And so I'm going to use this information to figure that out. So I want moles. I have grams. Very first thing I'm going to do, I'm going to determine how many moles I have of each species. I know I need mole-to-mole ratio, so at some point I'm going to have to find moles. So that's going to be my first go-to, is figure out how many moles of each species do I have. So number of moles of nitrogen. I'm starting off with 0.483 grams of nitrogen. I know based on my periodic table that 1 mole of nitrogen is 14.01 grams of nitrogen. Now we're going to get in shortly before you cover empirical formula in a regular chapter. We're going to cover naming, and you're going to find out that we have 7 elements that are what we call diatomics, meaning that in the natural world, they exist as a diatomic. Nitrogen and oxygen are both diatomics, which means the nitrogen around us, the air here is, I think it's 78% nitrogen is the average of nitrogen content in the air. Of course, oxygen that we're breathing is actually N2 and O2. When you're doing empirical formula compounds or calculations, you're not considering that. You are using the mass straight off the table. Probably doesn't mean anything to you right now, but absolutely is going to screw up some of my students come fall semester. So I just want to make it clear, you are using the mass straight off the periodic table at this point. And so 0.483 grams of nitrogen, converting to moles of nitrogen would give me, let's see, 0.03447 moles of nitrogen. And this has 3 sig figs. So I'm going to underline my sig figs here. That's how I keep track of sig figs, so I don't create round off error. I'm just going to underline it and deal with the sig figs by the end of my calculation. I also need the number of moles of oxygen I have. 1.104 grams of oxygen. 1 mole of oxygen. Look at the periodic table, and I see that oxygen is 16 grams per mole. And this will give me 0.06900 moles of oxygen. For sig figs, that's why I included the extra 0 here, because I need 4 sig figs here as well. Now I have the moles of each species. I am going to shrink that a little bit just for space. So now that I have the moles, I want to, so now I've got the mole to mole portion. Now I want the ratio. So I'm going to compare these 2 numbers. And I'm going to divide them specifically the moles by the smallest calculated value. I'm doing it by the smaller of the 2 numbers to guarantee that I'm getting whole numbers. This is what's going to produce that mole to mole ratio. Picking the smallest number is going to guarantee those whole numbers. So I compare the 2 numbers and I see 0.03447 is the smaller of the 2 numbers. So for nitrogen, 0.03447 moles. Means 1, obviously. Oxygen, 0.06900 moles of oxygen. 2.03447 moles from that nitrogen gives me a value of 2. So now I'm going to use that mole to mole ratio to determine the empirical formula. For every 1 nitrogen, I have 2 oxygens. I now have my empirical formula. That is the lowest whole number ratio of the 2 elements to one another. 1 nitrogen to 2 oxygen. Was the 1.587 grams of original sample useful? Not particularly at this point, but what if I had told you that I had a compound that contained nitrogen and oxygen? I said the sample weighed 1.587 grams, but I cut out this and said 1.104 grams of it was oxygen. What's the empirical formula of the compound? Now, if I did that, if I didn't give you that information about nitrogen, you could have found that by taking that 1.587 grams of sample, subtracting the grams of oxygen, and the remainder would be the sample of nitrogen. And there are questions like that in the homework, or like the additional practice that we offer in class. There's questions like that where we only give you part of the question because you can use other concepts from chemistry to figure out the other half. And so that's why I want you to see the different ways we can do this. Any questions so far? Okay. So empirical formula, again, an empirical formula, smallest whole number, multiple ratio of the elements. Now, percent composition, we're going to use percent composition. And normally in a regular semester, we learn percent composition right before we learn empirical formula. So percent composition is a percent by mass. How much of something do I have compared to the total mass of the sample? If I am given the percent composition and the molar mass of the compound, the problem is actually easier. And I'm going to show you what I mean by the 100 grams of unknown versus starting with 1 mole, et cetera. So we're going to work a series of examples today. But I want you to see one way you can do it if you are given the percent composition. So this is considered one of the challenge problems in the book. It does look a little more complex, but let's go ahead and work through it. It says chromium forms compounds of various colors. The word chromium comes from the Greek chroma, meaning color. Sodium dichromate is the most important commercial chromium compound from which many other chromium compounds are manufactured. That should say it is. I never caught that. I apologize. That should say it is bright orange crystalline substance. An analysis of sodium dichromate gives the following mass percentages. 17.5% sodium, 39.7% chromium, 42.8% oxygen. What is the empirical formula of this compound? Now, very soon, you guys are going to be practicing your naming, so you're going to know what sodium carbonate is anyway. Chromate. Chromate and dichromate are two different polyatomics that you guys have to have memorized. And so you would be able to figure out the formula of sodium dichromate just by knowing naming rules and knowing your polyatomics anyway. But you should be able to solve this mathematically as well if you're given these values. And so if me or Dr. Fry asked you to solve a question like this, you can't just give us the formula based on name, right? We're going to want to see the math of it. The thing is, this question has a lot of stuff to it. And that's one thing that students get overwhelmed with in the regular semester is we'll give you questions that have a lot of additional information. When I read this question, this is completely useless information. Completely useless information. Completely useless. Completely useless. Why do we have it in there? Because the real world gives you a lot of extra information and you have to figure out how to kind of sift through the information and figure out what's important. Students get really frustrated, understandably, because they're like, but there's so much to the question, I don't know what's important. I completely understand that, but that's part of what we're trying to do here in boot camp is train you to realize what's important and what's not. Now, this question is a little bit easier to tell what's important. Once you get more into the semester, sometimes it's really hard to tell. But again, our goal is to teach you guys how to tell what's important. Here, I've got sodium dichromate. I know that dichromate is Cr2O7 2-. I know sodium is Na+. Therefore, just from formula, I know that this must be Na2Cr2O7. So I know this could be my final answer. I know that's what I'm trying to get to. But again, I've got to do this by math. These are my percentages. This is what I'm trying to find. So that entire paragraph of stuff, I need 3 numbers and I need to figure out what I want to know. When we are given percentage, we're going to assume 100 grams of sample. This simplifies the problem for us a lot. If I assume I have 100 grams of sample, then I have 17.5 grams of sodium, 39.7 grams of chromium, and 42.8 grams of oxygen. It just makes the math easier. Just like before, I'm going to figure out the number of moles of each species. So number of moles, sodium, 17.5 grams of sodium. I look at the table and I see that 1 mole of sodium weighs 22.99 grams, which gives me 0.761 moles of sodium. I'm going to do the same thing for chromium and oxygen. So chromium, 39.7%. If I assume 100 grams, then I have 39.7 grams of chromium. I believe, yes, 52. I look up chromium on the table. Chromium is one of my transition metals, so it's in the middle of the table. 52.00 grams of chromium for every 1 mole gives me 0.763 moles of chromium. And my oxygen, again, 42.8%. If I assume I have 100 grams, then I have 42.8 grams of oxygen. 1 mole of oxygen weighs 16 grams. And this gives me 2.675 moles of oxygen. I'm now going to compare these 3 numbers, 0.761, 0.763, and 2.675. 0.761, 0.763 are pretty similar, but I see in the empirical formula that I'm going to have the same number of chromium to sodium anyway, so it makes sense. But I'm still going to pick the smaller of the 2 numbers to divide everything by. For sodium, 0.761 moles of sodium, 2.761 moles. Gives me 1. Chromium, 0.763 moles. Chromium to 0.761 moles. About 1. Why do I say about? Because mathematically it's not going to be exact, no, but we want whole numbers here. And so empirical formula does not always give you perfect numbers, but 0.763 and 0.761 divided by one another is going to be a value of 1. It's a 1-to-1 ratio. And I have oxygen, 2.675 moles of oxygen to 0.761 moles from the sodium gives me 3.5. Now, here's the problem. We can't leave this as a fraction. We want smallest whole number multiple ratio. Can't have fractions. So what we do is we're going to multiply all of our number of moles by some factor to make sure that they're all a whole number. If you end up with something that is 0.3, you're usually multiplying by 3. If you end up with something as 0.25, usually multiplying by 4. If you end up with something as a 0.5, you're multiplying all of those values by 2. This gives me 2 sodium, 2 chromium, 7 oxygen. Na2, Cr2, O7. And again, once you know naming rules, which actually comes right before this in the chapter, you guys would be able to tell quickly, check yourself and say, okay, yes, sodium dichromate would be Na2Cr2O7. But now we've proved it mathematically as well. Any questions?
Yes, can we just, instead of multiplying it by 2, can we just round 3.5 to make it 4, perhaps?
No, it will not give, first, it won't be the right answer. But 2, you're only going to round when it's actually really close. So like if you had like 3.9, absolutely. But if you have 0.25, 0.3, 0.5, you're always going to have to multiply by a factor.
Okay, thank you.
That was a really good question, Caitlin, because that's a common thing. Especially when you get more experimental data, the numbers don't work out as nicely. So you will have to round sometimes, like you've just mentioned. But yeah, if you have something that's like a 0.5, that absolutely has to be multiplied by something. Let's see. Next one, acetic acid is found to be 39.9% carbon, 6.7% hydrogen, and 53.4% oxygen. Determine the empirical formula. The molar mass of acetic acid was determined experimentally to be 60.0 grams per mole. What is the molecular formula? Okay. When you are, we can solve this pretty straightforward. We're going to solve it just the way we just did, but then we're going to also determine the molecular formula. Again, acetic acid, you should know how to do by this point anyway, because you're going to learn polyatomic acetate, and then you're going to learn how to name acids. So it's always a good way to check yourself. But when you're doing problems like this, but let's go ahead and solve it. We're going to do the exact same thing we just did. We're going to assume 100 gram of sample. And just to be clear, there are a couple different ways to do it when you've got the molar mass along with percentage. So you may have learned to solve this a different way. Totally fine. There are a couple different ways, but I just want to show the redundancy of what we've just done so you can see the correlation between them. If you know a different way and you want to check it with me, we absolutely can talk about that as well. If I assume 100 gram sample, that means I would have 39.9 grams of carbon. Carbon is 12.01 grams. This gives me 3.32 moles of carbon. I would have, let's see, hydrogen, 6.7 grams from that 6.7%. 1 mole of hydrogen is 1.008 grams. This will be 6.65 moles of hydrogen. And number of moles of oxygen. 53.4 grams of oxygen. 1 mole of oxygen to 16 grams of oxygen. Again, all these numbers I'm just getting off the periodic table. The 12.01, 1.008, and the 16. We don't expect you to have those memorized. You will have a periodic table on any assessment you do for class. So I've got the moles of each species. Now, just like before, I'm going to figure out the mole ratio of each species. So if I look at carbon, 3.32 moles of carbon. 3.32 is the smallest number. So that's going to give me a value of 1. I look at hydrogen, 6.65 moles of hydrogen to my 3.32 moles of my smallest number, gives me a value of 2. And oxygen, 3.34 moles of oxygen to my 3.32 moles. Again, we call that 1 because it would round to a total number of 1. I can see from this that my empirical formula is CH2O. I've got 1 carbon, 2 hydrogens, and 1 oxygen. I know the empirical formula, and I know the molar mass of the compound, and I want to know the molecular formula. So I'm going to shrink this for some space. The way I'm going to do this is I'm going to, okay, my empirical formula is CH2O. I'm going to figure out the molar mass. That fancy M like that means molar mass in my shorthand, by the way. I'm going to figure out the molar mass of this compound. If I added up 1 carbon, so 12.01 grams per mole, 2 hydrogen, 2 times 1.008 grams per mole, and 1 oxygen, 1 times 16 grams per mole. This is approximately 30 grams per mole. Not exact, I didn't add it up on an actual calculator, but approximately 18 plus 12 plus, or 16 plus 12 plus 2 is about 30 grams. I know the empirical formula weighs about 30 grams per mole, but I know that the compound says experimentally it actually weighs 60 grams per mole. This comes back to that, we talked about it in, I think it was chapter 2, but the ratios of the compounds always being in the same ratio. So it'll be a multiplet of this. If the empirical formula is CH2O, its molar mass is 30 grams per mole, then its molecular formula will be a multiplet of that ratio, because it's always going to be in the ratio 1 carbon to 2 hydrogen to 1 oxygen. My molecular formula — 60 grams per mole divided by my empirical 30 grams per mole gives me a ratio of 2. That means that my molecular formula is twice that of my empirical formula. So C2H4O2 would be acetic acid. It's the molecular formula molecular formulas are always, no exceptions, equal to or a multiplet of your empirical formula. Any questions on that? Okay. So let's talk through a little bit of a conceptual question. A friend has some questions on empirical formulas and molecular formulas. Letter A. For a problem that asked him to determine the empirical formula, he came up with the answer C2H8O2. Is this a possible answer to the question? If not, how can we correct it? I used these questions, similar questions this on an assessment, not last fall, but fall, what would that be? 2021. Fall of 2021 on the test, I believe it was their first test. I asked my students, depending on which version of the test they got, different conceptual questions like this. And students had a really hard time answering it. And so I want to talk through it in boot camp so at least you guys can see it before we get there. So if I ask a student to calculate the empirical formula, and they come to me and say the answer of their compound is C2H8O2, I'm going to immediately tell them, no, you cannot be correct. And the reason is empirical formula, it is specifically asking for empirical formula here. Empirical formula by definition is that lowest whole number or smallest, I apologize, smallest whole number multiple ratio. This is not it. I can simplify this ratio down. And so C2H6O2 may be the molecular formula, totally possible. But for the empirical formula, I would have to simplify this and say CH4O. And that's just really emphasizing that difference between empirical and molecular. For letter B, for another example, he came up with the answer C1.5H4 as the empirical formula. And is this correct? How can we correct it? No. Again, just like we just talked about for the definition, I know it sounds finicky, but it's very intentional we do it this way because we can take really complex questions. We'll work a couple more today as well, but we can work more complex questions and get the right answer, but we have to follow the rules of the game on it, which is smallest whole number ratio. So if I had C1.5 to H4, I would know I have to multiply through that to get to whole numbers. If I have a 0.5, I'm multiplying it by 2. 1.5 times 2 is C3. If I multiply 1, I have to multiply the other one as well. So H8. So if a student came up mathematically with C1.5H4, I would expect that student to recognize they have to multiply that, and then they would get C3H8, which is propane. You guys have probably heard of propane. It's propane gas. It's a common thing that we burn like in the big tanks and stuff for the grills. Let's see, letter C. The last example he worked, he needed to determine the empirical formula and molecular formula. He found the empirical formula to be C3H8O and the molecular formula to be C3H8O. Without information about molar mass, is this result possible? This one also threw my students off because they said, no, can't do. This is really bad spelling. It should be empirical. I can't even spell. I apologize. That should be say empirical there. But I apologize. My brain is so scattered. It's bad. But you can't. Sorry, the answer here is yes, the information is absolutely correct. Without the molar mass, I can't say his answer is wrong. But a number of my students said, no, it's not possible. My empirical formula cannot be the same as my molecular formula. And that is incorrect. They can match each other. The just base definition is empirical formula is my lowest whole number multiple ratio. C3H8 is the formula of propane. That is the molecular formula as well. That is a compound. So C3H8O, just a different organic compound, can absolutely be the molecular formula as well. Since we don't have information about molar mass, we cannot say it's incorrect. This would be a correct answer. So again, empirical formula, smallest whole number multiple ratio. Molecular formula is either equal to the empirical formula. So let me write that down. Molecular formula can be equal to empirical formula, Or 2, it can be a multiplet of the empirical formula. And that really threw students off. So I really just want to emphasize that, at least in boot camp, maybe not so much in class, but really in boot camp, I want to emphasize that. So you see, yes, they can be the same. Any questions on this? Another sample we do, and I know Dr. Green posted a complex or a more advanced question on the discussion board about combustion analysis. So another thing we do with empirical formula is combustion analysis. Combustion just means we burned the sample. So we take a sample, we burn it in a furnace, and then we monitor or collect how much comes off of it. We can, I know it's kind of hard to see the pictures here, but here we can see like, we've got, some kind of unknown sample being burned in a furnace. We've got the presence of oxygen being added to that sample, because when you burn something, you need an oxidant. Oxygen is your oxidant. It's adding oxygen to your sample. Burn it in the presence of oxygen. And then we can have a water absorber, a CO2 absorber, and we can actually absorb other substances as well. Sulfur, nitrogen, whatever you want to look at, we can absorb. But if I burn just a common compound in the in a presence of oxygen, I will produce H2O and CO2. And we haven't gotten to combustion analysis yet. That's chapter 4. That's really where we hit combustion analysis. We start balancing equations, so that'll be next week. But if I burn a sample, if it contains carbons, hydrogen, and oxygens, or just carbons and hydrogens, it always produces water and CO2. Those are always the products. That's considered complete combustion, and that's just what's going to happen. We can measure how much water comes off of the system. We can measure how much CO2 comes off the system. Why is that important? Because that can help us actually determine the empirical formula of the compound. So the carbon that was in our original sample has been converted to CO2. We use that mass of CO2 to find how many moles of carbon were in our original sample. The hydrogen that was in the original sample has been converted to water. So we can use the mass of water to back calculate to find the original number of moles of hydrogen in the original sample. Now, oxygen can be a little tricky. Oxygen is added in excess. So if our sample has oxygen in it, we're also adding extra oxygen to the system. So we can actually do kind of a backwards way of finding how much oxygen was in the sample. And I'll show you what I mean by that as well. To figure out how much oxygen was in our original sample, find the moles of that. If we're looking for nitrogen, we can look at collecting ammonia production in a separate sample, convert that back to how much nitrogen was in our sample, and other elements can also be analyzed in a similar fashion. Students hate combustion analysis. They tend to be a little bit more difficult of a problem to do, but they're also the ones that I don't know about Dr. Fry's classes. I don't write her quizzes and her exams, but if you look at my old quizzes and exams, I like combustion analysis. The students know it, so they just kind of remember how to do the process. But again, I know Dr. Fry has more students this year than I do. She has both sections. I only have one section this year. Normally it's switched. So you may have her instead. And I don't know if she cares or not, but I want my students to know how to do combustion analysis. Okay, so we've got quinone, which is used in the dye industry and in photography, is an organic compound containing only carbons, hydrogens, and oxygens. What is the empirical formula of the compound if you find that 0.105 grams of the compound gives 0.257 grams of CO2 and 0.0350 grams of H2O when burned completely? Given a molecular weight of approximately 108 grams per mole, what is its molecular formula? So what's important here? Not this. Not this. This. This is important. I know that my sample has carbons, hydrogens, and oxygens in it. So I'm going to be using CO2 to find carbon, H2O to find hydrogen, and doing some kind of back calculation to figure out how much oxygen is in my sample. What am I trying to find? I'm trying to find empirical formula. I'm told that I have 0.105 grams of the compound. That's important. 0.257 grams of O2 and 0.0350 grams of H2O. I recommend when you're studying these to highlight the important parts of the question. I don't care if you bring a highlighter with your quiz or exam, but it can help focus you back because you're going to spend some time reading the entire question. Then you're going to have to go back through the question again and say, okay, what was important? So the first step, read the entire question. Second step, go back, underline, highlight something, circle, I don't care. Identify in the question where the important parts are, because then you're not rereading the question 5 times. Just to be completely frank, when you guys have quizzes in class, they're 10 minutes. 10 minutes is not a lot of time when you're under stress. It is a lot of time when you know what you're doing. When you're doing exams, Dr. Fry takes care of all the exams for all of the students. I believe they're an hour long, but they may be 50 minutes. I can't remember exactly. I have to find, but I think that they think they're an exact hour. So again, if you're reading the question 5 times, you're not gonna have time. Let's see, it's telling you molecular weight, 108 grams per mole, and I want to know molecular formula. So I need to know empirical formula. And I'm told 0.257 grams of CO2, 0.035 grams of water. I need to know molecular formula. And I'm told 108 grams per mole. I know I'm looking for carbons, hydrogens, and oxygens. So step 1, use your CO2 to determine moles of carbon in the original sample. Again, I can't create nor destroy things. So if I can figure out how much CO2 I produced, I can back calculate to figure out how many moles of carbon that came from. All of that carbon produced CO2. It tells me in the question, burned completely, meaning that all of the carbon has been converted to CO2. So number of moles of carbon, I have 0.257 grams of CO2. I know 1 mole of CO2 weighs 44.01 grams, because I can add that up from the periodic table, 1 carbon, 2 oxygens. And now when I look at the formula of CO2, I see that there is 1 carbon for every 1 CO2. That is giving my mole ratio. 1 mole of carbon in every 1 mole of CO2. This gives me a value of 0.00584 moles of carbon. I'm going to do the same thing for hydrogen. Use the H2O to determine. Need to put that up. Moles of hydrogen. So number of moles of hydrogen, I start off with 0.0350 grams of H2O. Convert that to moles of water. 1 mole of water is 18.02 grams. And now when I look at the formula, H2O, I see I've got 2 hydrogens for every 1 water. So times 2 moles of hydrogen for every 1 mole of H2O. And this will give me 0.00194 moles of hydrogen. So I've got my moles of carbon, I've got my moles of hydrogen. Now the issue is, how the heck do I figure out how many moles of oxygen I have left? This is where conservation of mass comes into play. I know the compound itself weighs 0.105 grams. I know that compound is comprised of carbons, hydrogens, and oxygens. If I can figure out how many grams of carbon was in that sample, how many grams of hydrogen was in that sample, I know the remaining grams of that sample had to be made up by oxygen. And so that's what I'm going to do. I'm going to move this up so I can write down here. So number 3, I'm going to determine the mass of carbon and hydrogen and use that to find the mass and then moles of oxygen. But I'm going to do it in one fell swoop. You can do this individually. That's fine. I don't care. But I'm going to do it in one big calculation because it just makes my life easier. First, I want to find the number of grams of oxygen. I know I started off with a 0.105 gram sample. I'm going to subtract the mass of carbon. I know I have 0.00584 moles of carbon, but I know that carbon, 12.01 grams of carbon to 1 mole. So I know it looks funky the way I'm doing this, but this is my mass of carbon. If I was to actually calculate that out, it's hard to read that. If I was able to actually calculate it out, which I just didn't write down the numbers, I'm not writing it down for you. But if I calculated it out on my calculator, 0.00584 moles of carbon, converted to grams of carbon, that would weigh the amount of carbon in that sample. Caleb, 1 second, let me see. Thank you, Reagan. Yeah, that will absolutely. Hold on. I don't have a calculator on my desk. They're all at home. 1 second. Sorry. I absolutely did forget to multiply by 2. Thank you, guys. I don't know what I was doing. I have no idea what I was doing. But even in the notes I'm reading, I don't have it multiplied by 2. So thank you for that. What did you guys get? 0.00388. Thank you. That is more correct. Yes. Okay. Thank you for asking about that. Okay, so I've got the moles of carbon. Now I'm going to do the exact same thing, or grams of carbon. I'm going to do the exact same thing for the grams of hydrogen. So minus 0.00, what is it? 33388 moles of hydrogen times 1.008 grams of hydrogen to 1 mole of hydrogen. I'm running out of room. And I don't think I have the right answer written down. So 1 second, I'll actually write this down somewhere. This is the problem when I'm working these things out and I'm watching TV. Don't do your homework when you're watching TV, because then you write stuff down wrong. And then you have to quickly figure out the right answer. In 0.00422 grams. Normally I plug it all in a graphing calculator, which you guys are not allowed to use either. But all of my calculators are at home. Point 0.0701. I'm getting 0.0701 grams here. And I've got to write this down because I've got to calculate the new answers. 0.00422 grams here. Oh, hold on. Type that in wrong. 0.00388 times 1.008, 0.00391. Okay, so 0.105 grams minus that mass carbon minus the mass of hydrogen gives me 0.03099 moles of oxygen, grams of oxygen. Oh, I'm doing well today. I need to shrink this. This is also the advantage of not teaching online. I really don't miss it. I like doing boot camp. I really dreaded the entirety of COVID because teaching online, it's just not fun. Okay, now that I have grams of oxygen, I'm going to go ahead and figure out how many moles of oxygen that is. Times 1 mole of oxygen, 16.00 grams of oxygen. Gives me 0.00194 moles of oxygen. How do I have that number right on here? Anyway, I have that number right on my screen, but I had missed out hydrogen earlier. I really am sorry about that, but seriously, Kayla and Regan, thank you guys for figuring that out. Now I know my moles of each species. So Moles of carbon, 0.00584. Moles of hydrogen, 0.00388. Moles of oxygen, 0.00194. And divide all of them by the smallest number. I look at all three of them. I can see that of all three of them, the oxygen moles is the smallest. So I'm going to divide all of them by 0.00194. 0.00584 divided by 0.00194 gives me 3.06. I round that to 3. Let's see, 0.00388 divided by 0.00194 moles gives me about 2. And of course, this round of room just gives me 1. So empirical, C3H2O. I know my empirical formula is C3H2O. I've answered half the question so far. A lot of dang work, half the question. But I know that my molecular weight is approximately 108 grams per mole, and I want to know the molecular formula. So same thing as before, I'm going to add the molar mass up of this, which let's see what that is. 12.01 times 3, 1.008 times 2, plus 16. Getting the right answer. It's about 54 grams per mole. There are some decimal places there, but I just have to add it by head at this point because for some reason I'm entering the calculator wrong on the computer, and I apologize. But my empirical formula has a molar mass of about 54 grams per mole. My molecular formula is about 108 grams per mole. So same thing I saw before, my molecular formula is about twice as large. Now I can see that really easy from the math, but what if I couldn't? If I couldn't, I would find room on this slide. Good luck, right? 108 grams per mole divided by 54 grams per mole gives me a 2, which means the molecular formula is twice as large as the empirical formula. So molecular formula would be C6H4O2. Now I've got the empirical, for quinone, if I looked it up, I should find its molecular formula to be C6H4O2. Are there questions on that one? Okay. Also, again, I know I said already, but seriously, thank you. This most common thing missed. And like I said, even I wasn't paying attention when I wrote it out. So what you guys see on the screen is what I'm writing out actively on my iPad. What I'm reading off the screen is another PDF I've pulled up, which has the answers on to calculate it, guys, while you guys wait. And when I was doing it, for whatever reason, I just didn't pay attention. And I said 1 mole of H2. And so that's what messed up those numbers. And but that is the first thing that messes students up, is it just looks overwhelming and they just don't know the process. And I understand that it is overwhelming. There's a lot to it. Second thing that messes them up is they forget the 2 moles of hydrogen to 1 mole of water. Third thing that messes them up is this. They just don't see how to do it. If you get this process down, it just makes it easier. Okay. Any questions before I do the last problem? Okay. So caffeine, some of you guys love caffeine. Some of you guys swear off caffeine. It really depends on the student. But if you like caffeine, you know, it is a stimulant found in coffee, tea, and certain soft drinks. I don't drink coffee or tea, but I definitely drink soft drinks that contain carbon, hydrogen, nitrogen, or oxygen and nitrogen. So I know I've got these pieces in here. Combustion of a 1 milligram sample of caffeine. Combustion, again, means burning. And we're going to get more into this next week, but it's burning in the presence of oxygen. Reducing CO2 H2O, and then whatever else needs to be produced to finish off the compound. So in this case, N2. So I combust it, I burn it. I burn a 1 milligram sample and I produce 1.813 milligrams of CO2, 0.4639 milligrams of water, and 0.2885 milligrams of N2. I'm going to estimate the molar mass of caffeine, which lies between 150 and 200. So I know that if I get between that number, I have the right answer. First thing I'm going to do is figure out the moles of each species. And I'm going to have to shrink this a lot because I have stuff written everywhere. So number of moles of carbon. I've got 1.813 milligrams of CO2. That is milligrams. I need grams. I know 1 gram of CO2 contains 1,000 milligrams. Do I care if you show this step specifically? No, Dr. Fry may. I don't know. I'm not her. I don't care if students convert to milligrams right away. But so some students will do it this way. Some students will just write 1.183 times 10 to the minus third grams and start that way. Same thing. I don't really care. But again, if you have Dr. Fry, she may feel differently. She may want to see this stuff. I'm showing it to you so you guys can see the process. Let's see. This is giving me the grams of CO2. So now I need to go to moles of CO2. CO2 weighs 44.01 grams. And then carbon. 1 mole of carbon. 12.01 grams. Gives me 4.12 10 to the minus 5 moles of carbon. Do the same thing with hydrogen. Number of moles of hydrogen. I've got 0.4639 milligrams of water. I know 1 gram of water is 1,000 milligrams of water. I know 1 mole of water weighs 18.02 grams. And I know there's 2 moles of hydrogen for every 1 mole of water. Calculate that through, and I get 5.15, 10 to the negative 5 moles of hydrogen. Sorry. Number of moles nitrogen, because we do have nitrogen in this sample, 0.2885 milligrams of N2. 1 gram of N2 to 1,000 milligrams. 1 mole of N2 weighs 28.02 grams. And I have 2 nitrogens for every 1 mole of N2. Gives me 2.06 10 to the minus 5 moles of nitrogen. Now I still need to find the number of moles of oxygen. But first I have to figure out how many grams of oxygen I have. So I'm going to go ahead and shrink all this because we still got a lot to write. So we'll come back to that in just a sec. Let's determine the grams of oxygen in our sample. We can do it just like we did before, where I did it all in one fell swoop equation, or we can do it in multiple parts. This time I'm going to do it in parts. So you can kind of see the 2 different ways because students have different preferences on what they do. So I'm going to take that number of moles from above and convert that back to milligrams of each species. So number of milligrams of carbon, 4.12 times 10 to the minus 5th moles of carbon. I know I have 12.01 grams of carbon for every 1 mole of carbon. And I know I have 1,000 milligrams for every 1 gram. This gives me 0.495 milligrams of carbon. And do the same thing for hydrogen. 5.15 times 10 to the minus 5th moles of hydrogen. 1.008 grams of hydrogen for every 1 mole of hydrogen. 1,000 milligrams of hydrogen for every 1 gram of hydrogen gives me 0.0519 milligrams of hydrogen. Oops. Number of milligrams of nitrogen, 2.06, 10 to the minus 5 moles. Nitrogen, 14.01 grams of nitrogen to 1 mole of nitrogen. 1,000 milligrams of nitrogen to every 1 gram of nitrogen gives me 0.289 milligrams of nitrogen. So now I can go back to figure out how many milligrams of oxygen I actually have. Then I can go back up front or up top, figure out moles from grams. So if I have a 1.00, I guess here I was actually determining milligram. That's what I actually solve for. I have a 1 milligram sample. I know that 0.495 milligrams is carbon. 0.0519 milligrams is hydrogen. And 0.289 milligrams is nitrogen, which means overall I have 0.164 milligrams of oxygen left over. Now I can go back above and figure out how many moles of oxygen that actually is. So I have 0.164 milligrams of oxygen. One gram of oxygen. Hold on, forgot I shrunk that. It's not gonna work, and the font's gonna throw me off to bed. This works better. 0.164 milligrams of oxygen. 1 gram of oxygen to 1,000 grams. I know that 1 mole of oxygen is 16 grams of oxygen. And so I calculate this out and I get 1.03 times 10 to the minus 5 moles of oxygen. I'm going to shrink this down because again, we're still not even done yet. And I need some space. Now I know my moles of each species though, which is good. So I can use that to figure out the actual empirical formula and then the molecular formula. I know for carbon, 4.12 times 10 to the minus 5 moles. For hydrogen, 5.15 10 to the minus 5 moles. Nitrogen, 2.06 10 to the minus 5 moles. And oxygen, 1.03 10 to the minus 5 moles. I compare all four numbers, and I see that the smallest number is my oxygen. So my smallest number of moles is my oxygen sample. So I'm going to divide all of them by that value. Divided by 1.03 10 to the minus 5 moles gives me a ratio of 4. Divided by 1.03 10 to the minus 5 moles gives me a ratio of 5. Oops. Divided by 1.03 10 to the minus 5 moles gives me a ratio of 2. And of course, dividing by itself gives me a ratio of 1. I now have the empirical formula. My empirical formula C4, H5, N2O. So now I'm going to go ahead and add this up and figure out the molar mass of the empirical formula. I figure out the molar mass of this is 97.1 grams per mole. It tells me here, the last bit of information is that the molar mass is actually between 150 and 200 grams per mole. I can see my empirical formula does not fit into that. So I have to find some ratio that does. Doubling my empirical formula would give me a molar mass within that range. So if I take 2 times C4H5 N2O, my molar mass would become 194.2 grams per mole, which fits the range. C8H10 N4O2 would be my molecular formula. And so I was able to solve my empirical formula and my molecular formula through combustion analysis. Does that make sense to you guys? Do you have any questions? Combustion tends to be the hardest of them for students to do when it comes to empirical formulas and molecular formulas. The others, you'll see examples of both in class and on assessments. So, like I said, combustion or empirical formula itself, it's always whole number, multiple ratio. Combustion analysis, things students are going to forget is they're going to forget like the 2-to-1 ratio for hydrogen to water. They're going to forget how to find the oxygen in the sample, or they're just going to get overwhelmed by the question and not know where to start. So try to get these down, see if you can do them. Once you get the process down, it makes a lot more sense. And once you can really focus on, like I said, I focus on remembering the definition, smallest whole number, multiple ratio. And that is what really helps me remember how to do the math correctly, because I know I'm looking for moles. Once I have moles, I know I'm looking for ratios. Once I have ratios, I've got formulas. Okay, and that's all I have for you guys. If you don't have any questions, make sure to check out the other Zoom sessions this week and keep coming. Next week, we start week 4. So we're speeding up at this point, but the next 3 weeks will be chapters 4 and 5, which are a lot more intensive of chapters. Hope you guys have a good Thursday. Thank you.
Thank you.
I have a
Thank
question,
you.
Dr. Conrad.
Okay.
When you found the moles of nitrogen originally,
Mhm.
you used twice the molar mass, and then you multiplied by 2 moles of nitrogen per mole of N2. Why did you account for it twice there?
So nitrogen itself, like when we analyze nitrogen and collect it, we collect it as N2. It's a diatomic. So nitrogen itself has an atomic weight of 14.01 grams per mole, but N2 is twice that. So I had to do 28.02 grams per mole to account for the actual mass of what I call nitrogen in the air. And so like in the question, it says combusting as N2. Sorry, I know that there's so much written on this board. Combusting it as N2. So I have to use the 28.02 grams of N2 to account for how much was actually made of nitrogen gas. Now, in the formula itself, I'm trying to figure out exactly how many nitrogen atoms there are, which is that 1-to-2 ratio. Does that make sense?
Yes, thank you.
Other questions? And Reagan, the diatomics are going to throw a lot of students off. And so it really comes from context of the question as well. So like when I talk about nitrogen in general, generally speaking, not an empirical formula, I mean a diatomic, which is N2, which is 28.02 grams per mole. In empirical formula specifically, we always have to convert back to how many individual nitrogens are there, which is the 14.01. But that
I was trying to account for that, but I used the 14 grams per mole, and then I did 2 moles of nitrogen per mole of N2.
Okay, so you did that here? Is what you mean? Below.
Yeah, I use
Okay.
14 in the denominator.
Okay. So the 14 there won't work because that's not the actual molar mass of N2. And that's why you have to use the 28.
Okay, that makes sense. Thank you.
Yeah, no, that's actually a really good question. It's kind of like in here in the denominator for oxygen, I use 16 because it was just purely oxygen. It wasn't O2 at that point. And so that it's a good question. It's going to throw students off because it depends on what exactly I have at that moment to see which molar mass I want to use.
Got it. Thank you.
Yeah, thank you for asking. Any other questions from you guys? Okay, well, have a great week. I will see you guys very soon. We're running out of summer at this point. So I will see you guys next week. Thank you for coming.
Bye. Thank you.
Thank you.
Have a good one.
You too.